So we're going to look at position, displacement, and average velocity. Position is where we are according to some point of reference. There's a frame of reference. We've chosen a coordinate system. We've chosen how we're going to describe where a point is in that coordinate system, usually using Cartesian or plane polar coordinates. When we do this chapter, we're typically just sticking to one dimension. So in this case, our coordinate system looks more like a number line. And again, one-dimensional motion, we are restricted, so we can only move along one direction. In this case, we're going to move along the x direction. So our origin is really where we're going to describe each point in space. With regard to it, can be completely arbitrary, it can be a point of reference somewhere in a room, on the surface of the earth, whatever you want to use. But all motion will be described based on that particular position. Okay, so looking at displacement, displacement is where we started and where we end up. Okay, our final position minus our initial position would be defined as our displacement. In this case, it's one-dimensional motion, so we just describe our position in terms of x. It's important to note, however, depending on what frame of reference we choose, okay, our position may be different in two frames of reference. This top one right here, our origin's right here, and this bottom right here, the origin's right here. What does not change, however, at least we're not going relativistic yet, is that the displacement is the same in both cases. Displacement doesn't worry about what your position is. It's how much your final position has changed compared to your initial position. In terms of position and displacement, we're going to use whatever system of units that we're most comfortable with. For this course, almost everything will be in SI units, so it'll be in meters. But again, units can be in CGS units, which would be centimeters, or just customary, which would be feet. Just a few examples although these are very, very simple, to get comfortable with this. Here we have a truck moving from 10 meters from the origin, that's the initial position, to 80 meters from the origin. Okay, how would we write this mathematically? We would use a delta to represent change. Delta x is our displacement. Okay? Our final position is 80. Our initial position is 10. So in this, we move to 80 meters from the origin, from an original 10 meters from the origin, so our displacement becomes the difference between the two. Final minus initial. And the delta sign again symbolizes change. How much change has taken place? So position, where we are with respect to some frame of reference. Displacement, how much has that position changed? Now we'll go from 80 meters from the origin to 20 meters. Notice we're still doing final minus initial. But in the second displacement, our final position was smaller than our initial. Now our result is we have negative 60 meters. What does that mean? Well, this shows us how these coordinate systems work. In the x direction, positive is from left to right. Negative represents right to left. So the positive sign or the negative sign are indicators of direction. Okay? Positive direction, negative direction. All right? If we're talking about the distance that we've traveled, we'd never travel negative 60 meters. Again, distance is a scalar. It's how far you've gone. Displacement is a vector. How far and in what direction. In one dimension, it's easy. You're either going in the positive direction or the negative direction. Therefore, the positive and negative sign here are going to be the indicator of direction. Okay, so distance and displacement can be two different things. Very, very important. I think earlier on we did an example going from a campsite to a lake. and there are 3 different paths you could take, all might represent different distances. Okay? You can travel from point P to point Q a number of different ways. Okay? You can go directly there, you can travel, in a wavy path, you can go way up and then come down. The distance that you've traveled doesn't really have any impact on the displacement. The displacement simply asks, where did you end up compared to where did you start out? Okay? So distance and displacement are really 2 very different things. Displacement is really, what direction did you travel? How far are you from the original? I don't care about the trip. Again, one of the unfortunate things about this course is we will be changing notation from time to time. This is a pretty good example. We start out by using subscript F and I. Okay? Makes sense. Final minus initial. It's important to note that eventually we drop off the F because it's implied that X represents our current position. We will replace the initial with a 0, oftentimes called X0. Okay? So what does this mean? Does the physics change? No. Okay? We're just going to change eventually how we write this out. But again, final, it's implied that no subscript, that's the final of the current amount. I will be replaced with 0. Sorry for the confusion. This is a way that's been done. This is a way that's done in the textbook, so we're sort of stuck with it. Let's look at some displacement examples, and again, just get used to all the symbols that we use, all the nomenclature. Here we have a person walking from their home to go half a kilometer away. Okay? Now again, we live in a one-dimensional world in the examples that we have right here. So she's going from left to right. Maybe she's going east in this particular direction. Here we would say that our first displacement was 500 meters. Okay? Then she goes back home. So now we're going the opposite direction. A vector pointing in the opposite direction is the negative of that vector. If we've got 500 meters, now we're going negative 500 meters. Okay. Then after going back home, maybe she forgot something, she goes another kilometer back east. So now we have traveled the displacement of 1,000 meters. Again, the point of origin can be thought of as a home, or it can be something off to the left. Displacement is final minus initial. Her last displacement takes her from here, 1.75 kilometers to the west. Okay, now we see a number of displacements here. We see a nice little diagram right here. This is great. We have a visual of what's going on. We have all of our numbers right here. But sometimes it's helpful to take this information and to graph it to get a different perspective on what's going on. Okay? Here's our displacement. Now I'm going to add some extra information to this. First displacement, second displacement, third displacement, fourth displacement. There was no indication how long it took in each case. Okay. Let's now say that in each of these cases, there was a certain amount of time that went by. Okay? Originally she started at home, then it took 9 seconds to go half a kilometer. Well, I think I'm going to have to change that example. Maybe traveling in a car. Well, whatever. We'll stick with what we have here. If you're running 500 meters in 9 seconds, you are putting a cheetah to shame. But in any case, all right, we'll just use this example and go with it. Even 500 meters in 90 seconds would be impressive. We're stuck with what we got. So here are the different times. Now, displacement is your change in position. In these cases, this is where I ended up. Okay? If I now graph this, it should have been time in minutes, I apologize. Somewhat more reasonable. Okay? In any case, I don't like this so much because I like using SI units, but it's in minutes. But you can see she moves east, then she moves west, then she moves east even further, then she moves west even more. Graphing position as a function of time is very important because it allows us to see the rate at which this change is taking place. Okay? Notice that the uphill here and the downhill here, what we call slope, was pretty gradual. Maybe a little bit steeper here and a little bit steeper here. Okay? That rate of change will be very important later on when we talk about velocity. The slope here represents how much your displacement is changing as a function of time. Okay? Rates are very important in physics because rates represent how a system is evolving as a function of time, and larger rates obviously indicate a much faster change. Again, displacement isn't distance. Displacement includes what direction, how much your position has changed. And use an example here. Distance can actually be greater than displacement. You throw a ball up in the air and then it lands back in your hand. If you do the displacement of where it was when it started and where it ends up back in your hand, that displacement is zero. But yet the ball has traveled a distance twice as much as the height that it reaches. Okay, I answered my conceptual question. An object, let's say a car, goes from one point in space to another. After it has arrived at its destination, its displacement is, an object goes from one point in space to another. Is the displacement either greater than or equal to the distance? Always greater than the distance? Always equal to the distance? Either smaller or equal to the distance, either smaller or larger? Well, again, what did I say? Displacement can be zero, right? Throw a ball up, catch it, its displacement has no change. But yet it's traveled upward and then come back down. So the distance can be greater than displacement. Distance can also be equal to displacement, so I would say displacement is either smaller or equal to, and that's our answer. If you've ever traveled to Washington, you've got a great example of this. Washington has this big beltway around it, okay? You want to get from somewhere north of Washington to somewhere south of Washington, the last thing you want to do is go right through Washington. Actually, the beltway oftentimes isn't much better. But you would probably pick up this beltway and go around, which would be a greater distance than the distance between where you started and ended up. So your displacement would be small, even though your distance might be twice as great. Actually, looking at that, it's nearly circular. Your distance would be about 3 times greater. Okay, so far, what do we have? Position, where you are. Displacement, how that position has changed, in what direction. Now we're going to go back to that idea of slope. Okay, the rate at which we change. That is speed. Okay, actually it's going to be velocity, but we're going to start with speed. Speed asks a question of how much ground you cover per unit time. What is the total distance? What is the total time that goes through? Speed is a scalar because it never asks what direction you're going. It simply says, how much distance are you traveling? How much time did it take? When you look at the speedometer of a car, it's usually reading miles per hour or kilometers per hour. You can drive in circles and that speedometer isn't going to read zero. Okay? So average speed is how far given the amount of time that you travel. For SI units of speed, we use it's the MKS system, so we're going to use meters per second. Speed is always positive, the way that we define it, because you can't go a negative distance. So distance divided by time. And again, a very good example of this would be a car. Think about a trip computer that you might have on a GPS, on your phone, built into the car itself. In this particular case, the car has traveled 55.69 miles. Okay? The time that it took is 2 hours, 7 minutes. So we can calculate what was the overall average speed. 55.69 divided by, get to convert minutes into hours. 7 minutes is roughly a little bit more than a tenth of an hour. So, you're roughly divided by 2.1. So 55.69 divided by 2.1 gives you 26.2. In fact, it gives you a few things. You're only moving for 1 hour, 50 minutes. Okay? Again, you'd have to do a conversion there. But again, 55.69 divided by, 1.85? I don't know. I'm thinking. Gives you 30.2. Again, you could have been traveling much faster than these averages. Top speed here was 76.8 miles per hour. And sometimes they were stopped. In fact, they were stopped for 16 minutes and 49 seconds. Okay? So distance divided by time, that gives you your average speed. Okay. Typically, the symbol for speed and the symbol for velocity can be interchangeable. We usually use V. If we really want to differentiate a velocity from speed, we'll put a little arrow on top, but sometimes you'll see these used interchangeably. Quick calculation, 400-meter race is done in 1 minute. We want everything in SI. So 400 meters, we convert the 1 minute to 60 seconds. How fast did this person run? 400 divided by 60. Here we're looking at a rate. How far? How much time? 6.7 meters per second. That's a pretty good time, or a pretty good speed. Okay, about the fastest that a person can run is roughly about 10 meters per second, about 22 miles per hour. Convert this into miles per hour. Remember, anytime we do a conversion, we want to take the units that we start with, multiply it by conversion, where the units we want to convert to is on top, the units that we want to convert from is on the bottom. That's about 15 miles per hour. Of course, we can calculate distance from speed and time. Just rewrite this equation as distance is equal to speed times time. Person runs at a rate of 5 meters per second for 3 minutes. How far did they run? 900 meters. Convert that to kilometers. You want to convert that to miles. You can, again, just do it by conversion factor. Now at this point, speed and velocity in this one-dimensional world, there's not a lot of difference between the two, other than there might be a positive or negative sign because we're going one dimension. Okay? But you can pretty much do the same thing when you're calculating one-dimensional velocity. Just distance divided by time, is fine. And again, calculating time, and convert this equation this way. Okay, let's go back to this concept where our displacement to the right is going to be positive, our displacement to the left is going to be negative. So, again, much of what we went over is going to be, the same here, except for a positive and negative sign indicating direction. When we graph, we should understand that the slope of the graph, the change in the vertical axis divided by the change in the horizontal axis, will give us velocity when graphing displacement as a function of time. Now, again, I say distance. Probably should have used displacement, but we'll go with this. In these graphs, in these motion graphs, a very steep slope will indicate a high speed or high velocity. Okay? Smaller slope indicates a lower speed. Got to correct that right there. So for instance, in this first case right here, if I do rise over run, I can pick a point 60 meters on the y-axis and pick a distance of 4 seconds on the x-axis, I could have done the slope anywhere. You know, here I can go over 2 seconds and I can go up 30 meters. I'm going to get the same result. During that rise over run, I see that my speed is 15 meters per second. If I'm traveling in the positive direction, that'd also be my velocity too. In this case, I have a lower speed. Okay? I'm traveling at a constant rate, so you see a straight line. Okay? That indicates that my speed, my velocity doesn't change. And again, I apologize for using speed and velocity interchangeably. For this discussion, it works. Here the rise is 30 meters, the run is 12 seconds. 30 divided by 12 is 2.5. I could also have done a rise of 10 meters over 4 seconds. 10 divided by 4 is still 2.5. Okay? So in these types of diagrams, it will tell you what the motion is at any time. Again, in one dimension, speed and velocity, there's not a whole lot of difference here. Notice it's moving from 0 to 3 seconds. Okay? It's moving at a constant rate. If you do the slope there, it's at a rate of about 10 meters per second. Now, the position doesn't change. For this case, there's no slope, it's stationary. Again, we go up, it's increasing its distance, so we have speed, we have velocity. If we want to graph something that is speeding up, the speed, the velocity are represented by the slope. So notice the slope is pretty gradual right here. You can imagine if this were a hill and you're climbing up, it'd be pretty easy to climb. As you go further and further, notice it gets steeper and steeper. Okay? Get to the point where it's so steep, you think about the slope right here, it'd be a difficult climb. Same thing, low slope, low velocity. So we're getting steeper and steeper and steeper, we're speeding up. So looking at these motion diagrams, where we see a curve like this, that indicates increasing speed. Likewise, which is the opposite, here we're steep here, and we're less steep here, that indicates that we're slowing down, lower velocity. Let's do a graphical interpretation of average velocity versus, in this case, this is actually, when I was talking about that, I was talking about a different term we're going to get later on to, instantaneous quantities. Here, because we had a straight line, the speed, the velocity was constant. Okay, a curved line indicates that it's changing. What is happening at this instant is known as instantaneous, in this case velocity. What happens over a trip is what we call average. Now in this case, we're going to graph position as a function of time. All right? Right? Different positions at different times. If I want to know what was my average velocity traveling from A to D, okay, I notice that my slope goes up and my slope goes down. Slope at that point, instantaneous slope, is instantaneous velocity. We'll cover that in a little bit. But I want to know on average what happened on this trip, just like the trip calculator that we saw before. Okay? I actually go forward and then I go backward in this example. But if I look, I start at about 50 meters from the origin, and I end up a little under, well, roughly about 90 meters. So 50 to 90. Okay, I had to do the calculation in my head. I was getting a little scared. We were off here. So my rise here to this point is 40 meters. My run here is 3 seconds. Now you say, oh, wait a minute, I actually went farther than this and then I came back. Now, average is final minus initial. My final is 90, my initial was 50. 90 minus 50 gives me 40. Doesn't matter that I went even further than that. an average value asks, compare the final to the initial. Okay? Time, 0 to 3 seconds, so that's going to be my run. 40 divided by 3 gives me 13 meters per second. And we say positive, because velocity we're worried about, increasing position, decreasing position. We're worried about direction, 13 meters per second. And again, my average velocity will be different from A to B, A to C in this example, A to D in this example, and A to E or A to F in this. Actually, A to E and A to F are pretty much the same thing, so I take it back on that one. Here my velocity average, my average velocity is positive. Here my average velocity is barely positive, it's almost 0. Here my average velocity is negative, and here my average velocity is very negative. Okay? So when we're calculating average velocity, graphically what we should be thinking about is a straight line that goes from the beginning point to the ending point. And the slope of that straight line is what our average velocity is. See, the slope of this straight line, this blue line, was our average velocity. Okay? So one way to think about average velocity, I think we call this a secant line, is a secant line that goes through 2 points. Now again, velocity is displacement, okay, delta x. Delta x can be positive or negative in this one-dimensional universe. We can go forward, we can go backward, divided by the change in time, okay? What does the clock read finally compared to what was the clock before? A lot of times we just make the initial time 0 anyway, so we don't even have to do a calculation difference here. But delta t represents change in time. How much did time change as our position changed? And again, here's an example of the truck. It goes from 0 to 80 meters, has a displacement of 70 meters. Let's say it took them 10 seconds. That would be plus 7 meters per second for my average velocity. In the second case, I go in the negative direction. So my displacement is negative 60. I do that in 10 seconds. So negative 6 meters per second. Okay? And again, positive versus negative, that's just indicating what direction I'm going in. Again, for velocity, it's displacement divided by time. Displacement's units in the SI are meters. Time is seconds. So we use meters per second. Just customary, we'd use feet per second, miles per hour, CGS, maybe centimeters per second. Just as distance and displacement may not be equal, displacement's a vector anyway. Speed, being a scalar, might not be the same thing as velocity. Okay? Going from point P to Q is going to have a different displacement. So therefore, when I calculate the velocity, displacement divided by time, I will get a different value. Speed is distance divided by time. So I can go a greater distance than displacement for the same given time, so my speed might generally be a little bit faster. So again, straight line indicates a constant velocity. In this case, the velocity is constant. That means that my average and my instantaneous values are going to be the same. Again, we did this already, so we'll skip through all this. Going back to the person going back and forth, and again, I made the correction later on. If we want to calculate the velocities for each of these cases, I converted our minutes into seconds and read to this graph. Notice that when we're moving in the positive direction, the slope is positive. We go 500 meters in 540 seconds, so that's more reasonable. About 0.93 meters per second for this first slope right here. Now for the second part of the trip, it's going to be downhill. Okay? Now negative 500 meters, We do that in 540 seconds, so we get slightly different times.